Okay, so welcome to lesson 10, last lesson from the refresher course. Well done for sticking it out to the end. So today I'm going to talk about functions and then inverses, and then we're going to get into the intro to calculus. So basically differentiation from first principles. And what I want to say about functions, first of all, is that in a way, like I guess let's consider what you've done so far, like what we've done so far, right? In this, so we've done some algebra, right? We've done some, trigonometry and coordinate geometry. Let's just call it geometry, right? Just generally geometry. Coordinate geometry's got some algebra in it, right? Because we have these equations to use and stuff. And then we also have, we did, statistics and probability, right? I'm going somewhere with this. What we're going to look at today will be calculus, right? And then we've got like little smaller topics like sequences and series and stuff like this, And I guess the point about it is like functions. Is this like a new topic, right? And the reason why I bring it up is because we've already seen functions. Like this is what kind of got me when I was doing Leaving Cert and stuff. Like why the kind of emphasis on functions essentially as if it was its own topic, right? Because what we see with functions is that it actually it's a little bit of algebra because we've seen like, f of x is equal to like x squared plus like 3x plus 2, and then we had to factorize that. So like this is a function, right? And it's like like we can use algebra on it, right? So we're used to having functions like using algebra. And then in coordinate geometry, you might have to like take this thing and I'd say, okay, well, what's the roots of this? Like x plus 2, like x plus 1. So that's x is equal to minus 2, x is equal to minus 1, and it's a U shape. So now we can go ahead and graph it. And there it is, like with the roots like minus 1 and minus 2, right? So it's also, let me put sort of graphs in here with like geometry. It doesn't necessarily belong there, I know, but you know, so it also kind of, we could also say that functions is spanning these two, and then also it spans sort of calculus. So what we want to think about functions isn't really kind of a new thing. It's a little bit of an application of the stuff that we've already been doing, okay? And just like quick, I know you already know this, but like the way to think about a function is just like a number machine. We'll call that number machine f, and we put numbers in and then we get numbers out, and the numbers that we get out are called f of x. And then for the purposes of making graphs, we can always take pairs of input and output values, right, which is the x and f of x. Sometimes we call it x and y, right? So it could be x and y that's coming out, right? And then we have like basically an axis then for like a horizontal axis and a vertical axis. And then for the horizontal axis, that's where we put those input numbers. And for the vertical axis is where we put these output numbers. And then, we could also call it like, the x-axis and the y-axis, or you could also call it like, the f of x-axis, right? It could also be called the f of x-axis. So what we can do with this is that we can take this input and put that one there, and we can take the output and then we can put it here, and then we get a point, and then we're able to graph the function. And when we graph the function, then we're going to be able to see something about the function that's maybe kind of interesting. So let's just like take an example, like f of x is equal to x squared, like let me just think of a couple of numbers, minus 4x plus 3. Okay, so I want to graph this thing now. Okay, so this is a function. I'm going to use algebra to get the roots. Okay, so that's like x, and then like minus 3 and minus 1. That's the same sign. Okay, and if I want to get the roots, so that's just me factorizing that function. Now, if I want to get the roots, I have to set f of x equal to 0, which means that x minus 3 by x minus 1 is also equal to 0, right? Which means that x is equal to 3 and x is equal to 1 are the two roots. So we can go to 1, we can go to 3, and we see that the coefficient here is a plus, so we have a U shape, right? Okay, like that. So we're going to draw a U shape that goes like this down and goes through there, like this. Okay. Now we want to look at this now in a few different ways. So let's have a, so what I was saying was like functions are kind of, you know, they're kind of, it's like a sort of like an application that you can, that draws a little bit from algebra, a little bit from like graphing, and a little bit from calculus. Okay, so we'll see this now, right? So let's think about the algebra first. So where's the algebra? Well, the algebra is happening here and happening here in order to like get the actual roots. That's where the algebra is happening. And the graphing, like the geometry bit, like the graphing bit, right? That's happening when we put the points down, right? And so for that, so we can draw this, you know, we could get lots of points in. We could say like f of 0 is equal to 0 squared minus 4 times 0 plus 3 is equal to 3. And then we can get our input, which was 0, our output, which was 3. So we go along to 0 on the x-axis, 3 of this is the number 3. That's where it crosses the axis. And then we can say, let's put in 2, like f of 2 is equal to like 2 squared minus 4 times 2, like plus 3. So this is going to be 4 minus 8 plus 3. This is equal to minus 1. So we've got the point 2 and minus 1. So we go along here in the middle and we realize that that there is at minus 1, right? That point there. Okay, so that's where the graphing's coming in. And what about the calculus? Like, what about calculus? Like, what's that telling us? Okay. And what calculus is telling us, you know, we use calculus because we want to look at like how things are changing. Okay. Like what we want to ask ourselves, like basically, if we were on this point here, like what's going to happen next? Basically, we want to be able to see, like, okay, you know, on the next step, we're going downwards and we're going downwards with that slope. Now, the thing about a curve, like a straight line, right? A straight line will have the same slope the whole time. So it just works y2 minus y1 over x2 minus x1. It doesn't matter which 2 points. You could pick these 2 points. You could pick like, you know, these 2 points. It doesn't matter because the slope never changes. It doesn't matter where you look, right? But it does matter if we look here, this is the slope, it's 0. If we look here, this is the slope, it's positive, right? And then we see like very strongly negative values like plummeting down. Then we see it sort of rises out and it kind of goes up. So we're interested with calculus, like in how things are changing, okay? And that's what we're going to be looking at eventually with functions, okay? So it's just, the reason why I'm speaking like this is because a lot of the time when students look at functions, they kind of think, oh, this is like a new thing. And it's a weird thing that happens. Like we're kind of like, you kind of imagine that you must not be understanding it because it couldn't be so simple. But it is just, it's just the stuff that you were doing before with a slight different emphasis, basically, so that we can kind of talk about input, output pairs, and we can talk about, you know, but we're using algebra, we're using graphing, we're using, and this will be useful for calculus and stuff. Okay. Okay, so understand functions. Let's sort of tick that one off the list, right? Let's say we've understood at least a bit what they are. Just put a number in, put a number out. That's the only thing. We'll talk a little bit more about some other restrictions, constraints in a second. Okay. The next one, inverse functions, right? So that's going to be important, right? Graphing, okay, we talked about that, and identifying the domain and range. Like this will be important, right? This is more to do with the picture, okay? We're going to talk about using the completing the square. So this is like a little trick, you know, it's a trick for handling quadratic equations. Basically, we can take any quadratic and we can split it into we'll be able to take, yeah, we'll be able to take any quadratic and we'll be able to split it into, we'll be able to write it a different way where we can find the turning point really easily, not using calculus, right? If you've done this already, you might realize we can use calculus to find the turning points, and then we're going to look at the slope of the tangent for the first principle. So that's the goals for this lesson here. Now, the other thing that happens when you go to study functions, right, is that the notation starts to get a little bit wild. So let's just have a look quickly at the leaving cert. Yeah, I don't want to scare you, right? But I'm just going to show you quickly, like, you know, you start to get into territory where questions have a lot of notation stuff come up. And you look at it and you think, like, why is it so sort of heavy on this stuff, you know? Like, you see this type of stuff, right? You're looking at this kind of going. Now, I promise you, this is not a big deal. Like, none of this stuff is a big deal, like this extra stuff. But it's just something that comes up that we start to use. It's kind of, I guess it's sort of, you can think about it as like, it's a like functions are like a mathematical application of like algebra and graphing and stuff like this. So we're really starting to speak a bit of a mathematical language here when we start to use functions, right? So it's like a mathematical application, as I was saying. So you can kind of see some stuff that we start to have questions with, which are more heavy on notation. Um, okay, the first one is like this idea of function, like function f of x. Even the name function is kind of weird. But basically, like it'll be f of x, and what we're thinking about is just basically like you put a number in and you get a number out. So you got your input and you have your output, and then you have like, you know, your function will always be something here on the right hand side, and it can be anything, right? So it could be like 2x squared plus like x plus 1, or it could be like some sine function and things like this, or it could just be a single number like 3 or a 0, meaning that no matter what value you put in for x, you always just get the same number out. So that's just like a horizontal line. Like if it was 3, it would just be a horizontal line at 3. Okay. Now, let's quickly talk about the domain. Okay. So the domain, okay, so we say x, y, you know, domain and range. I don't know if you can say like domain. So there's a D and there's a or for the range alphabetically, domain and range, right? X and Y. Okay. So the domain basically means what are the allowable inputs into this function? Like what can this function machine take in? Like you might say, well, the domain is x is an element of or, like it's just any real number, right? But you could say that x is an element of or, and you could add the condition that x is greater than or equal to 0. So that's just a positive real numbers. Or you could say that x is just a natural number, right? So this should be kind of like, yeah, like, you know, if this was a real machine, you know, like if I had a machine for making, I don't know, like screws or nails or something like that, you can't put in wood into it, right? You can't put in, so there are some constraints, right, on like what you're allowed to put in. And we're going to say that's our domain. The domain is what we're allowed to put in to the function. And the range is the sort of basically the set of values that we get out, right? So what we might say is that, you know, how can we think about it? Let's say I have a function which is called, how would we write it? Let's say f of x is equal to round. This is not really mathematical notation, but round, it's more like a computer science type thing, isn't it? Round x. So we could put into this function 1.9, and then we would get out 2. And then we could put in the number minus 3.2, and then we get out the number minus 3. And we could put in the number, you know, pi, which is 3.14, and we get out the number 3, and so on. Okay. And so what we see is the numbers that can go in, we could say that any number can go into this function. X is an element of or, that's the domain, right? However, here, the range is just set, because there's, when we round the number, we get a whole number out. We only get integers out. Okay. So we'll see this happening in a minute. So what you can think of when you do a function, another way to think about this is, let's say, like when you're faced with tons of notation, like if you're able to turn this stuff into a picture, then it's just like totally awesome. So so let's do a quadratic function, okay? And I'm going to basically draw like points in the, so this point went in, right? And then it went down, to the axis, and then it went across over here like this, right? And this point went in, like let's say that point went in, it came from here, right? It went up to the axis and it came across over to here, right? And then, you know, like we can keep on doing this. So we can keep like finding values, right, from, and what we find is actually all of the values on the x-axis can go in, you see? Like it might look like it, right? If we put in a point here and we go up, it's like we're missing the graph, but that's only because I ran out of page. This is going to keep rising up, and there will be a place where it will hit. No matter how far back we go, we will be able to hit this curve because it'll keep rising up forever. So in this case here, let me write down for the domain is basically x is an element of or we could say that or with the extra stroke. Or we could just say that the domain is just or. It's just any number can go into this function. But what about the range of this function? Well, the range is going to be, again, we get into the, like, because it's domain and codomain, but just basically think about the outputs that kind of come out, right? So it's actually not the entire of it, because we don't get down here at all, right? So this is kind of like the values that come out, right? If that makes sense. So we can just, you look at functions like this, and then we could tell that. But if we had a line, for example, like if we had a line like this, then it's the whole x-axis is the domain, right? So the whole the whole x-axis is the domain, and then the whole y-axis is the range, right? Now there is the codomain bit, which technically you're allowed to have all the y-axis, but in practice you may not get the whole of the y-axis, and that's what we mean by the codomain. But just think about the domain refers to the numbers that can go in, what's allowed to come in, what's allowed to come out, or what comes out type thing, right? So, okay, so now we get on to this thing here, injective, surjective, and bijective, okay? So we get those topics down, then we can talk about inverses, and then we can actually find inverses, and then we can also kind of graph them and stuff. And yeah, that's just fine. And then we can actually get on to doing some proper algebra, right? So there's another thing that we have to say about functions, right? So what's the rule for functions? So the rule for functions, right? So you have a function which is like some number machine, right? You put a number in, you get a number out. What's inside the box? Well, we would write it algebraically, right? That's the machine, 3x plus 2 or something like that. Okay, so the domain now is the numbers that are allowed to go in. The range is the numbers that are allowed to come out. And then there is so we put in an x and we get out an f of x. Okay. Now there's one major rule about this function, and this will actually make a kind of a split in terms of some of the coordinate geometry that we did with graphing and what we're saying. And the rule is that if you put in one number goes in, right, you're only allowed to get one number out. Okay, so let's try it with this one. F of 1. One number went in, 1 squared plus 3 plus 2. 3 times 1, which is 6. So 1 went in and a 6 came out. Okay, so one number in, and this number that went in came from the domain. This number that came out came from the range. Okay, but look at this function. I'm going to write down another function. F of x is equal to the square root of x. Okay, let's say we put a 2 in. 2 goes in. Sorry, 4 goes in. So x is equal to 4. The square root of 4. Then a 2 comes out, but also a minus 2. Okay, so this is not a function. Okay, so this is not a function unless we say that the range is the only x greater than 0. Then it's a function. Okay, so we're not talking about anything new here. All I'm saying is now we're playing a game called functions, and I'm giving the rules of the game, and the rules for the game are mathematical rules that we've been talking about in previous sections. Okay, so that's that. Okay, so now let's be a bit clearer then. Okay, so let's say if we have a function here like this, let's think about something. Let's think about some kind of expression that I could write down. Like, okay, let's think about graphing f of x. Well, let's just think about this idea in particular. So what I'm going to do is I'm going to draw something from coordinate geometry. I'm going to draw a circle. Okay. Now we can write down the equation of the circle. Could be, x minus h all squared plus y minus k all squared is equal to r squared. And this here is my hk. Okay. Now we could rearrange this, right? And we could get, after a little bit of algebra, we could get y on its own on one side. It would have a big square root on the other side, right? And this could then, we could think about that thing as being a function because, you know, the function, we can have f of x on the left-hand side, but we could also just call it y. You know, the reason why we use the notation f of x is this idea of a function that you put a number in. That's why we have, this is like, you know, this is almost like f, like having x as input. That's why it's written this way, right? But you can just write it as y, and then it's just not as explicitly clear that it's a function, but, you know, we understand that it is. Okay, so we could take this function, get y on its own on one side, and have this. So what's the problem? Why is this not a function? Well, let's just take any specific value of x. So let's take this value of x. Let's say that it's 7. And if we put 7 in and now go to the curve and try to recover the y value, so we can go here, or we can go up here to hit the curve, and then we go across, you see, like that. And this is like my y1, and this is like my y2. So you see, for this particular function, then this one, let's call it, now, why don't we give this function a new name? Because we keep g, let's call it g of x, because we keep, that's another thing with functions. We call them f, we call them g, we call them h, we call them t, we call them every letter, right? So you have to be prepared potentially. Usually for some reason they make it like tall letters, you know, but they can still make it. It's weird that this stuff catches us out, but that's it, you know. Okay, so our function is called g. And what goes into our function? Well, we put in the number 7, went into our function. And what came out of the function, like y1, y2? Uh-oh, not a function, because it had 2 outputs. Okay, so the function has to have, but there's an even a simpler way to think about this. If you go ahead and draw an xy axis, so this is your xy axis like this. So we go ahead and we draw an xy axis. Now I'm going to draw a function. So I'll draw, okay, this one, this is a yes, right? This, yes, it's a function. And then in this color, it'll be like no, not a function. So no function. Okay, so okay, so this one is a function. So what I'm going to do is go like so on. Okay, do what it does, whatever it wants, right? We don't know what, I don't know what will give us this, right? Like what is it? Quadratic? Is it going to be square? I don't know. It's sines, cosines, exponentials, squares. What, I don't know, but I know it's a function. Why do I know it's a function? Well, let's draw something that isn't a function. So this one takes a similar type of path, but then look. Okay, what happened? For some piece of it, I was moving back. So for the function, we always need to be able to drift from left to right. We can never go from right to left. As soon as we go from right to left, then if we made any vertical line, it would cut the, see, it would cut in more than one place, you see? And then we would have, for that particular output, we would have 3 separate outputs, and we're breaking the rule. So functions can never double back on themselves, okay? However, there is no such rule in this direction. That's fine. We can have a value of y that has that is given by multiple values of, like, you know, of x, like this x1, this x2, and this x3, right? So we can have multiple inputs that can give the same output, but we can't have one input that gives 2 different outputs, okay? Now you might ask the game why, but just think of a board game. Let's just think of any board game, like, I don't know, pick one, anything. There's just going to be some rules there. And if you're going to play the board game, you have to follow the rules. So this is not a fun game necessarily, but this is a tool that we use, and this is the functions, the rules of functions that we have. We have this. Okay, so now let's talk about injective and surjective. I'm sorry if I'm taking a long time with this. The reason is I've been tutoring this for like years and years and years, and also at university a lot on this topic. And there's just so much mystery around what the hell are they talking about, and there isn't really so much mystery there. The problem is that it's really kind of, it's written essentially in a kind of a foreign language. It's written in a maths language, which is why it confuses so many people. Okay, so let's talk about injective. Now watch this here for a thing. I just want to make sure that I'm right about this. So for injective, we're going to say, if x1 is not equal to x2, that implies that f of x1 is not equal to f of x2. And this is true for all x1 and x2 an element of OR. That's the definition of injective. That's horrible, right? This is what I mean. Let me explain what it means in really simple terms. So let's pick an x1, and an x2. Just two random x1s and x2, right? What it's saying is if these two are not equal to each other, then their outputs that go over f of x1, f of x2 are also not equal to each other. And that's not just true for these particular two. Slide this x1 all the way up and down the axis, slide the x2, pick every possible combination, and it never happens. That's still not a satisfactory answer. Okay, so and this is what I really want you to do when you come across things that are complicated, right? This is what we need to do as sort of humans, I think. Basically, what does this thing mean? It means no bubbles. That's what it means. Does that make sense? Just think about it for a second. If I'm always rising, even if I'm sort of like meanderingly rising, not necessarily like a straight line, or it could be like an exponential curve. If I'm always rising, then there's no point where there's the possibility that because if x1 was going to be the same as x2 and they were a distance apart from each other, then I'd have to go up and come back down, you see, for that. I'd have to have a bubble or a bump or something. So what does injective means? No bubbles. I prefer this explanation to this one, right? The reason why this one's important is because it comes a time in your study of maths where you kind of need to kind of step over into speaking sort of fluent kind of maths, but like you don't have to be plunged right into it, right? And that's why this type of explanation. Now, what does it mean? X1 is not equal to x2. So if x1 happened to be equal to x2, here's x1, and then x2 they're equal to each other. So of course the outputs of the function are then equal to each other. Okay. Now, what about the next one? Now, the reason that this is going to happen. Let me show you why injective is important. Let me do a trick here for you. So if you can see here, this is the graphic software that I use. Okay, let me draw something, right? So I just drew something, and then I undid it, and then I redid it, and I undid it, and I redid it, right? So this is basically like it's any tool is only useful if we can undo it, right? So if we have addition, well, we have subtraction. So we add 2, then we could subtract 2, so we could undo the work, right? If we have multiplication, then we have division, right? If we have like exponential x, then we have log to the base e or ln of x, right? So we have ways for every single mathematical kind of thing that we do. It's nice to have some way to undo it. Well, let's talk about functions. We're about to talk about inverse functions, right? Now, let me draw a function which has a bubble. So this is a function that is not injective. Let me draw it without the x's. This is a function that's not injective. Okay. Now, so when we basically work out, when we take this function here, we're going to see this probably in a second. Put that over there. Okay, so we draw the xy axis, and then we draw the xy axis again, or whatever, something like this. Okay, so we draw, this is the x-axis, this is the y-axis, and the function takes in x and it coughs out y. Okay, so it takes in this value of x here, and it coughs out this value of y here. Okay. Now the inverse function, what does that do? Well, it actually does the opposite. Now we have the y-axis here and the x-axis here, and this one actually takes in the y value and coughs out the x value. It undoes. So if here we pop from here to here and go over. Actually, that's a bad example. Let me jump from. Let's jump from here up here, and we go over to here, right? This is the value of x we put in. This is the value of y that we get out. Now, if I started here and wanted to go back to that point there, you see I'd hit the curve and I wouldn't know where I came from. So if the function is injective, you have this. If it's not injective, you have this bubble. And then when you turn it on its side, you see, then you have this problem that it's no longer a function because you have, for each of the inputs, you're going to have multiple outputs, okay? So that's why we care about injective. Ultimately, we care about inverse functions. So injective and surjective are all about inverse, okay? So what's surjective now? So let me just give you my my other type. So the surjective is basically all of the range is mapped to. So I'll give you an example of a function that's injective. This function here, that's injective. Why? Because for that function, the domain is OR and the range is OR. So the domain, what values, it's the x-axis, what values are allowed to come in, these ones, and then which are the ones that come out? These ones. See, so all of the axes. I'll give you another function that is surjective. See, all of the axes here is mapped to. We don't leave anything out for, this would be a cubic function. This just keeps on going down and down and down, okay? I'll give you an example. If for example, my range is OR, okay? And if I had a parabola, then the bottom of the parabola is here, right? So that's my range. And I don't map to, I leave out like this whole piece of it and all the way down to infinity. So I've stopped there. Now imagine that was a number -1. What if I said my range was -1 to plus infinity? Then it's okay. Now it's a surjective function, okay? So you see we're playing around a lot with definitions with this. And okay, so let's talk about the last thing. So basically, if a function, so we'll take a function f, if it's injective, no bubbles. If it's surjective, then it's bijective, meaning it's surjective and injective, which means that it's invertible. And we can find f inverse of x. Okay, so let's think of an example. Okay, so why is that important? Well, let's just think of a function. So we draw a function, and then we have, this is an x value that goes in. This x value, it rises up, it hits the curve, and then it goes over and coughs out a y value. Okay. And then if we wanted to go back and undo what we did, we could start with that y value, go back and arrive back at the same x value. Okay. Now let's imagine if we had a different one, like one like this. And now we're going to put in, so this one is injective because there are no bubbles, and it's surjective because you have the whole line. And then you can see that it has this pattern here. Now imagine we put in this x value. We go across and we get out a y value over here. But now we start with the y value, we try to go back and we land in 3 different spots. So because it's not injective, because it has a bubble, that makes it not invertible. Because we need to know, like if we go from x to y, then we need to know what it is. We need to like know where we came from. So just jump from this x to this y and then back again. Okay, great. So I should move on because I've been on this for a while. Now, and the last one then is like, yeah, if it's not surjective, so if it wasn't surjective, so let's pick a function that's not surjective, then like, and we're going to say that the range is OR, and we're going to say the domain is OR. So we take f of x equal to e to the x. So it's never negative, right? So it goes up like this. And yes, if we put in a certain value of x, if we put in this value of x, then we get out like this value of y. Or we put in this value of x, we get. But the problem is that once we try to go back, we'll never be able to get any value. Like if we put in these y values down here, we'll never find an x value that gives us that. So that's it's not surjective then. Okay, so let's have a look. So the inverse is basically you have to be able to go back, and then what we're going to do is basically in practice where we have y and f of x, just as what we're going to do is just swap the x and y and then solve for y basically, and then write down f inverse of x. So let's just try that. So we're going to say that I mean, this is a trick. There's probably other ways that you've been told. So you write down this here, and then you swap the x and y, and then you can solve that's equal to 2y, and that means that x minus 5 over 2 is equal to y. Okay, so that's that trick. And then from here, then you can write down that f inverse of x is equal to x minus y 5 over 2. So we have then that f of x is 2x plus 5. We have f inverse of x is equal to x minus 5 over 2. Let's just try it with the number 5. F of 5 is 10 plus 5 is 15. F inverse of 15 is going to be 15 minus 5 over 2 is going to be 10 over 2 is going to be the same number back out again. So that's what all of this is about. Okay. Okay, good. So, and the last, very, very last thing is that basically when we talk about graphing inverse functions, f of x and f inverse of x, if we're going to graph them on the same graph, well, what we have here is we make a plot y, sorry, we make a plot of like y is equal to x, right? We just make that line, or f of x is equal to x. We just draw that line. Now let's say I'm going to draw f of x first. So f of x will be in green. So let's say f of x looks like this. Okay. That will mean that f inverse of x will be like this, a perfect reflection in that line. Okay. Okay. So that's basically everything that you need to know for that topic. Hopefully I didn't go on too long there. Okay, so as I said, domain and range were the allowable input values, and now we can talk quickly about the completing the square trick. And I think we'll just have enough time to talk about differentiation from first principles. Okay. Okay, so this is actually dead easy, completing the square. All it is you have a quadratic written in this way, and you write it in this way. Okay. What is this way? Well, you have, this is called a perfect square. So if ever you have like x plus 2, for example, all squared, this becomes x squared plus 4x plus 4. Or x plus 5, all squared, it's x squared plus 5x plus 25, okay? So what, sorry, plus 10x plus 25. So what you're looking for, or we'll try another one, x minus 3 all squared, this is equal to x squared minus 6x plus 9. So what you're looking at is the coefficients of your quadratic. Okay, you look at the b and the c, and you realize that the c is two numbers multiplied together, and the b is those same two numbers added together. See, this is 5 squared, this is 5 plus 5. This is 3 squared, this is, oh wait, this is minus 3 squared, this is minus 6, okay? Now, if you take any quadratic, like we could take the one that's written first here, x squared plus 6x plus 5, well, this can be, we can look at the first like two terms of this, right? And we can look at that 6 and we can say that 6 is our b. So that's a, we have to look for b over 2 plus b over 2, you see? And then that third number, if that was b over 2 by b over 2, then we would have a perfect square. So what I'm going to do is just do this magic trick. And this is all there is to it. 9 minus 4. X squared plus 6x plus 9. Put that stuff in brackets. X plus 3 all squared minus 4. Now, why is this useful? Like, why is it useful to do this? F of x, x plus 3 all squared minus 4. And the main reason, I guess, it's sometimes you can just do things with it kind of like quicker, but basically you can find the roots and the turning point like much faster, right? But let's okay, let's find the roots of this real fast, right? F of x is equal to roots. F of x is equal to 0 is the roots, right? So that tells us x plus 3 all squared minus 4 is equal to 0, right? That tells us x plus 3 all squared is equal to 4. Now take the square root of both sides. X plus 3 is equal to plus or minus 2. That means that x plus 2 is equal to 2, in which case x is equal to x plus 3. Sorry, I thought I made a big mistake. And I was, okay, x is equal to 1. X plus 3 is equal to minus 2. X is equal to 5. Yeah, 1 and 5. 6 makes sense. Perfect. So we can find the roots dead quick from this. And the other thing that we can do is we can actually just look at it, right? So if you see it for a second and see this square, see, anytime I see a square, an equation or in brackets, right, I just know whatever that is, it's positive. Like that's what squaring does. Squaring kind of makes things sort of, changes and makes them larger. If they're less than one, it makes smaller, but kind of makes them larger most of the time, I guess, but it makes them positive. This is all positive, okay? So we have this thing at the back, which always has this positive thing added to it. Okay, so basically the smallest f of x can be happens when this bit is 0. And you're just left with that minus 4. Otherwise, if this bit is not 0, it's positive and it's added to the minus 4. Think minus 4 might be minus 4 meters under the water. This is a positive thing added to that, so it's raised up a little bit, right? Okay, so this square is always raising it up from its floor, okay? That means that, well, what makes this minus 3 makes this 0. So we get immediately the bottom of the quadratic happens at minus 3, minus 4. Now, why don't we always do this? Why isn't this our way of solving quadratic equations? It's just a little bit, I don't know why it is exactly, but like basically going from 5 to 9 minus 4 kind of messes people up a bit. It's like, I don't know where you got that from, right? And you have to be very targeted. You have to look at that 6 and you have to say to yourself, this is two numbers added together, 3. And what are those two numbers when they're multiplied together? 9. And then recover then the perfect square and then subtract off the other number, okay? It's just a trick. It's very simple. And just once you understand this example completely, they might put in a minus here and there. Do you know what I mean? But it's very, very hard for anyone to trick you on this ever again, okay? That's all there is to it. Okay, so finding roots from completing the completed square equal to 0 and then solve using square roots. So this is just what I said. You can either find the roots or you can find the turning point at the bottom. You can find, they call it the vertex. Even the vertex, I don't know where I got that from. It's not really a vertex. We've been using vertex for the corners of triangles and squares. So, just forget about that word. It's just the minimum, let's call it, or the maximum, or the turning point. Okay, so basically when we have, that's really the point. So when we take a quadratic, and every quadratic can be written, it's just a matter of breaking the last number into two other numbers, and one fits into the perfect square bit, so we can write a perfect square. Once we have that, we can graph it because we have the two roots. So, if you have the two roots, let's say the two roots are like, whatever, like 1 and 1 and 3, and you have the minimum, which is like 2 and minus 5. Then you can go over and we'll also, from the quadratic, like we can just look at the number, like this a here. If that a is greater than 0, we have a U shape, right? So then we can go over, we can put down 1, we can put down 3, and then we can go to 2, and then down to minus 5 and put that point there, and then we've got 3 points, and then we can go ahead and sort of, we can graph the parabola here. So we can graph the parabola there, right? Because if we didn't have that bottom point, this is a parabola that goes through those 2 points, but so is this, and so is that, right? You know what I mean? So then we need the bottom point also, and then we have a good sketch of the parabola. Okay, so let's get on to slopes and rates of change. Okay, and this is, we just have like about just about 10 minutes to get into this. And what I want to show you is this formula here, okay? Now this formula here, it's another one of those types of mysterious types of formulas. Let me talk about this here, straight line, and finding the slope of this line here. X2, y1, y2, okay? What's the slope? Y2 minus y1 over x2 minus x1, okay? Now, if we have a curve, and that doesn't matter, it could be any x1 or any x2. Now, if we have a curve, the point about it is that, you know, you have to think about, imagine this was like you're out for a walk in the mountains or something like that. So when you're here, you're going uphill and it's steep, and then you've reached the top of the hill, and then you're like running downhill, and then you're going back uphill again, and so on, right? So the slope is ever changing. We know that. It gets steep, it gets less steep, it goes up, it goes down, it goes flat. These are intuitive concepts. But what do we mean here about the slope of the curve? Well, if we have a point in the curve, then we're going to be able to draw any number of lines that go through that point, right? Like that one goes through there, that one goes through there, right? But there's only one that does this, you know, like skipping a stone on a pond. There's only one that basically tips the curve but doesn't cross the curve, okay? And that's true at every single one of these points. Now, it could happen, for example, if we were at this point, let's say this point here, right? I don't know. If we were at this point here, right? And let's say we wanted to, let's say we wanted to get the tangent to that curve there. So we go along, we get the tangent, but look, we've crossed the curve over there. So this is the tangent to the curve, even though we crossed the curve in another place. Well, what we mean about crossing the curve in another place, what we mean is like locally, right? In a small little area, and that actually small area is actually microscopically small, like brackets that just go right around the point. And in that little area, it doesn't cross the curve. For every other, it crosses it right where the point is, if that makes sense. So we want to be able to work out the slope of the tangent to that. We want this M1 here. We want this M2 here. We want to have a way to get that slope there. Now, because we're short on time, I'm not going to prove this, but I can write this as, well, I can write it as f of x2 minus f of x1 over x2 minus x1. If I now interchange, you know, instead of calling it the y-axis, I call it the f of x-axis. Then instead of having y1 and y2, I could have f of x2 and f of x1. It's just different notation. However, if I now think about this as x, and I think about the gap between the two as h, then this would be x plus h, okay? And then when I was to write this formula, then it would be not f of x1, it would be f of x, and not of f of x2, it would be f of x plus h. So that would be f of x plus h minus f of x over h. So this formula here is just the slope formula, y2 minus y1 over x2 minus x1, except for this piece. Okay, this is the mysterious piece. This is the kind of the brilliant piece about calculus, basically. And what it does, what that limit as h goes to 0, you see, finding the slope always involves 2 points, right? And the limit as h goes to 0, let's say we want to take this point here. Instead of that second point that we're going to use this formula for in a slightly different form, being far away, we make it infinitely close to the other one. So close that actually the 2 points that are on the white curve, the 2 red points that are on the white curve, are also on the purple line. So there are 2 points that are on the tangent, and then we can go and use the slope formula. But you have to understand that although these points here are 2 separate points that are like, you know, one's here, one's there, like imagine that you had a second point that wasn't off over here that was beside this one, that was infinitely close to this one. In fact, was the smallest imaginable distance that you could be away from the previous point, without being away from it, okay? So that's in theory. That's where this formula comes from. You can just say it's y2 minus y1, x2 minus x1, when x1, y1, and x2, y2 are infinitely close together, not any distance apart whatsoever. If they're a distance apart, then it's coordinate geometry, then it's this formula here. If they're infinitely close together, we don't use this formula, we use this formula, and we have this piece here. Okay, great. So how do we use this in practice? Okay, this is the good news. Well, unfortunately, I believe that you have to remember this formula. Let's, I've covered that. So let's go to an example. Okay, so what I want you to do, in order to, so we're going to be searching for f prime of x. And I think we just have enough time to get this done. So that's good. I did plan, this is what I plan to do today. So, you know, we just managed to get it in on time. Okay, so this is what we're after, f prime of x. Now, what is f prime of x? Remember, f of x is an input, a number, you put numbers in, 1 in, you get 1 squared out, which is 1, 2 in, you get 4 out. This allows us to make a graph of this function called x squared. But what is f prime of x? F prime of x is a machine, a number machine for getting out the slopes. So we can put in 0 and we'll get the slope here. And we can put in 1 and we'll get the slope here. And we can put in -1 and we'll get the slope there. We'll get the slope of the function. Now, in order to get that, we need to get the whole of the right-hand side here. So what I often do is actually just write down f of x plus h. Then I say, what's f of x plus h minus f of x? Okay, and then I divide all of that by h. So just do it in separate pieces. Now, the entire objective is to get that h off of the bottom line. Okay, that's all you have to do. And then you basically just sub in this number for h. Okay, so let's have a look then at f of x is equal to x squared. We're running out of time. F of x is equal to x squared. Okay, and this is the formula that we're going to apply. Okay, this one over here. Okay, so what is x plus h? Okay, so what is hold on, what is f of x plus h? Okay, well, it's just, this is the rule of functions. Okay, whatever is in here, it's just sometimes you know, whatever's in here, x plus h, you just sub it in place of x, and if it's complicated, just use brackets. Okay, that if you can get that, then that is going to save you so many problems, not only in the Leaving Cert, but just generally in maths. Whatever is in here, just go straight in, and if it's complicated, put it in brackets. Okay, this gives us x squared plus 2hx plus h squared, and then I have f of x plus h minus f of x. You see, what I'm doing is I'm gradually filling up that top line there. X squared plus 2hx plus h squared minus x squared. Why don't we just go ahead and divide by h? Divide by h, okay? And this is the thing that happens always when you do this. You see, on the top line, we have things that don't have x in them, and we have things that don't have h in them, and we have things that do have h in them, and everything that doesn't have a h cancels out, and everything that's left has a h. So that means that we can cancel. We cancel the h with the first one. We have 2x, and then we cancel the h one. H squared divided by h is 2x plus h. Okay, and the last bit is we just take the limit as h goes to 0 of f of x plus h minus f of x all over h, and we just say, well, it's a limit as h goes to 0 of what we just got on the above line. And all this means, it means that h, we're not saying that h is equal to 0, right? We're saying that h is approaching 0 and actually gets infinitely close to 0 without being 0. And what h is, if you recall, h is the gap between the 2 points. H is the gap. So we're saying limit as h goes to 0. It's like, it's like the limit as h goes to 0. We're saying let the gap get infinitely small, right? That's what we're saying with that statement. So we're not saying h is equal to 0. We're just saying h is getting infinitely close to 0. But in practice, we just say it's 0 when we do the thing. So this is the answer. Okay, so f prime of x is equal to 2x. Now, we just have 1 minute, so I can go ahead and graph this thing. So f of x is equal to x squared. Sorry, starting to scroll now. Is equal to x squared. F prime of x is equal to 2x. Okay, so let's try and x is equal to 0, 1, 2. No. let's take x is -2, -1, 0, 1, and 2. So this is like f of this gives, I'll just make a table, right? So this one will be f of x here, right? And then this will be f prime of x over here. So what we have here is, well, I put in 0, I get 0 out because it's just squared. I put in -1, I get 1 out. I put this one and I get 4 out. I get 1 and I get 4. And then I get, well, this one here, x, when x is -2, I put it over into this one. So 2 times -2 is -4. 2 times -1 is -2. 2 times 0 is 2. 2 times 1 is sorry, 2 times 0 is 0, sorry. 2 times 1 is 2, and 2 times 2 is 4. Okay, so now I have the points from here. Let's write them: -2, 4, -1, 2, 0, 0, 1, 2, and 2, 4. So these are my points, and then I have the slopes. Like here is a -4, here's a -2, here's a 0, here's a 2, here's a 4. Okay, just a moment this will take, and then I think we can stop then. So let's go and say that this is -1, this is -2, this is 0, this is 1, this is 2. So this is now 1, 2, 3, and 4. And here we go. And here we go, and here we go, and here we go, and here we go. So this is the function here, okay? That's a function here, right? Okay, and let's have a look at these tangent lines. So here's a tangent line. See, there's a tangent line. And here is 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 a tangent line. Okay? And what this whole thing now is telling us is that so the slope of that tangent line is -4. That makes total sense. This is like a steep, this is more than 45 degrees down, right? This one here is, that is m is equal to -2. This one here is m is equal to 0. This one is m is equal to 2. This one here is m is equal to 4, okay? So not only do we have a function that gives us out, you put a number in and you get a number out, not only do we get that, we now have another function which tells us what's going to happen on the next step. So we could say, we could put in -2. We could get, okay, when it's x is equal to -2, y is equal to 4. But then we also know, yes, but it's going to go down after that. So imagine you're a shop and you're like, okay, I'm going to put in, x means a day of the week, and, y means the number of people who've come to the shop, and it's like, well, there's going to be 20 people in the shop on Tuesday. But then the other thing is, yeah, well, after that, it's going to go down. That's predictive. That's okay. Well, tomorrow I won't need as much staff or as much stock or whatever. Okay. So anyway, that just unites together the whole thing. So I'm just going to ask you something quickly. If you could manage to take out your phones and scan this QR code, you're going to be brought to a page to do a Google review for me for these things here. So in short, I'm trying to start. Trying to start these. This is a business, I did this refresher course to, kind of do a free refresher course. That I'll let you know about lessons coming up, like group lessons like this. That's coming up, about €20 lesson. I'll let you know about that in the coming days or whatever. But in the meantime, if you have your phone on you and you could just scan that QR code quick, you'll be brought there. And I've got a few reviews there, but like every review, yourselves, it's like really crucial to get good reviews, or else people don't find you. So anyway, I hope my lessons were helpful to you. Yeah, if so, just you have my email and everything. You have the address if you want to do more lessons during the year. I'll be doing like maths and physics. Maybe I think I'm doing a physics one. I'll be doing like maybe applied maths, but I'll be doing a few different maths ones on different days, and you can find one that suits you. Yeah, and then also, yeah, spread the word. Let your friends know. People are always looking for a good tutor. So if you like these lessons, then let people know. And then and thanks very much for your for paying attention for the whole course. And then yeah, hope to see you again then soon. Okay, bye bye.